We're going to investigate enzymes. Recall that enzymes are proteins that specialize in catalyzing chemical reactions. One enzyme you've likely heard of is lactase. And maybe you actually haven't heard of lactase so much as lactose intolerance. Lactose intolerance is an issue around the world, as we can see from our figure. And what lactose intolerance is the inability to break down lactose. And lactose is made up of two sugars, and so our body naturally breaks down lactose into smaller ingredients to be digested. If we cannot break this down into these smaller ingredients, that can result in intestinal distress. And many people around the world actually have this. In fact, many people lose the ability to digest milk after about ages 2 to 5. So this figure right here shows us the amount of lactose intolerance broken down by country. And it can range from anywhere about 4% of the population up to 99%. And we can see that some folks who live in places like Scandinavia have a relatively low occurrence of this. Other folks who live in parts of Africa and Asia have a more higher incidence of this. Right? So 99% of people cannot digest milk, at least not properly, without age. Other places like the United States, Canada, Russia, Australia, again, it's closer to about 40%. But nonetheless, it is a problem. And again, why is this a problem? Lactase, a naturally occurring enzyme, for whatever reason, is not working in the human body, and that can cause issues. So lactase is one type of enzyme. The International Union of Biochemistry and Molecular Biology, they actually classify enzymes in 6 different ways. Right? So we have 6 different types of enzymes that we can use. One of them basically just a type changes the charge state of a molecule or an atom, and those are oxidative reductases. Transferases can actually transfer a whole group from one molecule to the next. Hydrolases actually break bonds, and this is what lactase is. Lactase breaks down the bond between two sugars. We also have lyases, which form or break double bonds, isomerases, which change molecules, and ligases, which actually join them together. Right? And so these are examples of types of enzymes, the classifications. A couple of specific roles that enzymes take. Number one, they can catalyze metabolic reactions, and so these are all the reactions that form in terms of breaking down nutrients or actually building nutrients up. They play a key role in blood clotting, digestion of food and nutrients, as we just talked about with lactase, and also the immunological response, and so this is dealing with viruses and bacteria and other things in our body. So those are just a couple of many types of things that enzymes actually do that you may have heard of in the body. So let's go back to lactase, the enzyme, the hydrolase. Here's a figure of lactase. Right, so this is a human protein. It's another organism too, but this one's an example of human. This one's about 160,000 Daltons, so it's sort of a medium-sized protein. It's a single polypeptide. Notice this one, its crystal structure is shown here in A, and there are different parts of it which have different colors. So again, it's all one polypeptide, but they're just showing different regions of this. Right? So one protein. Now remember, an important thing about enzymes is that they all have active sites. And remember, this active site is a small part of the protein, the enzyme, where the reaction takes place. So catalyze the reaction right here. And this is what's shown here in part B, a close-up of that active site. Recall our sort of rule of thumb is that about 10 amino acids make up an active site, and you can probably see that that's about right. These are not quite a whole amino acid, but it's getting close. And so around this lactose, which is right here, we'll have about 10 amino acids or so. It's a rule of thumb, and nonetheless it works. And this is what catalyzes the breakdown of lactose into the two products. Well, what are those two products? Well, here is the chemical reaction. And so again, we see our disaccharide, so that means 2 sugars. Here's 1, 2. They're connected by this beta-1,4 linkage. This particular connection, we'll get to that later in the course when we talk about carbohydrates, but nonetheless, it's a disaccharide, 2 sugars put together. Lactase, again, is the enzyme. It's here, shown above our reaction arrow. Notice it's a hydrolase, so water's involved in that breakdown of this bond right here, this beta-1,4. And notice the product of this is D-galactose and D-glucose. These are 2 monosaccharides, so they're broken down. And this is naturally what lactase does in the body. Right? And so again, if it can't do this, then that's when it results really in this intestinal distress. But here we see that. We're going to work with lactase today, and so we're going to break down this. We're going to look as it's just like in this reaction, to break something down. One of the things that if we use just lactose in the normal substrate for lactase, we'll get lactose and glucose, and that's not real easy to see either visually or any other way. So one of the things that we can do is we can use what we call an analog of lactose, and this is something known as ONPG, and this is an analog of it, and so we see it here. And notice it has one residue that looks really much like the other one, like a galactose, but then there's this other compound, which we'll call a nitrophenol, and it's attached there. Lactase, while it typically acts on just one or very few substrates, it will act upon this ONPG. The utility of doing that is that when lactase breaks it down, again with water, just like it would normally, we get galactose, one of its normal products, but then we also get this orthonitrophenol, and this orthonitrophenol is yellow color. So we go from a clear colorless solution to one that has a little bit of a yellow color, and we can visually see it, and then we can actually measure the absorbance of that in a reaction. So it allows us to say, all right, is this lactase actually active? All right, so is it actually catalyzing the reaction? If we just use lactose and glucose, it wouldn't be as obvious. We could still test. It would take a long time to test for individual components of lactose and glucose. If we use this ONPG, we can tell almost immediately because we'll start getting a yellow color that'll form. All right, so lactase degrades this. So some goals of this experiment are, number one, we're going to isolate an enzyme. All right, so we're going to isolate it. We're going to use some commercial tablets that contain lactase for people who have lactose intolerance. We're going to assay, we're going to measure the enzyme activity. That is it actually doing its job? I'm going to use that using a spectrophotometer. We are going to look at the temperature impacts of lactase, right? So we're going to see, does lactase work the same in ice as room temperature, maybe a little bit hotter, right? So the temperature impacts are going to be important. And then another way of thinking about the temperature impacts is we're going to assess the thermal denaturing conditions. So basically taking a protein, heating it to such a high temperature that it actually breaks apart, much like, at least it unfolds, much like you think cooking an egg in a skillet, it goes from clear to white because you're basically denaturing or making those proteins fall apart. We're going to do the same thing with lactase. We're going to see how those temperature impacts the denaturing impacts its activity. So as we start to work with the enzyme, its assay and activity, again, we're going to use spectrophotometer, and this is basically using light, colored light, visible light that we can see to produce, and we're going to be able to measure that quantitatively, how much light is being produced as lactase is breaking down the ONPG. And again, we're going to use temperature to see how that impacts the activity of lactase. In this first part of the experiment, we're going to isolate lactase from a commercial product. So again, why do we have these commercial products? For people who have lactose intolerance and they want to still consume milk and other dairy products, but still need to break down the lactose, this lactase in a pill form can actually do the same thing. Just by swallowing it, it takes the place of the natural. All right, so we're going to take out one of the pills from this, and we're going to put it into a mortar and pestle. And mortar and pestle, your pharmacist in the old days might have used this, but to mix medicines, and in this case, we're just going to homogenize it, that it is the pill into a powder form. What that allows us to do is to mix the powder then with buffer, as basically water that's been set at a pH of 7.5 with phosphate, and because lactase is soluble in water, and particularly soluble around pH of 7, we'll be able to extract the lactase from the pill. Right? So what that means, again, is that the solid lactase that's in the pill will then become in solution, much like you would find it in the natural world, dissolved in water. Right? So we're going to get a good bit of this powder out. Some of it's going to fall on the table, and that's okay. We're not even going to say exactly the amount. It's here. Right. So we got most of that out. So we have this labeled suspension, and we're going to take 10 milliliters of our phosphate buffered saline. Right, so this is water. We've added some phosphate to keep it at a pH of 7.5. The salt, the saline part of it, just helps to give a normal physiological salt concentration. We're going to use this vortexer to actually mix it up. This is a mixer, so it creates a vortex in here. So again, we're mixing the solid and liquid. As I stop it, you'll see that the solid is mostly mixed throughout. But this puts the solid into contact with the water, that is the phosphate buffered water, and allows the lactase to go from being in the solid to being in the liquid, which is where we want it. So anywhere from 30 seconds to a minute or so is just great for that. So now we have a solution. It's a little bit more than 10 milliliters of our solid mixed with the buffer, so it's mixed throughout. And so we're going to take 1 milliliter of the solution, we're going to pull it out. Right? And because we're just going to need a small section of this, we'll cap that back up. And we'll put that suspension into our microcentrifuge tube. And this microcentrifuge tube contains part of it. And we're going to put this microcentrifuge tube into our microcentrifuge. And I've already got a counterbalance that's in there to offset that. Put the lid on, the metal lid here, then we'll close the top lid. We're going to set this to 10,000 revolutions per minute, and then we're going to turn it on for a minute. What this is going to do is it's going to allow us to separate the solid from the liquid. Because we vortexed the mixture, much of the lactase went from being in the solid pill to being dissolved in the water. That is the phosphate buffered saline, the buffered water solution. So when that happens, we can now centrifuge this, and the solid's all going to go to the bottom, leaving the liquid above. So we're effectively separating the solid, what remains of the pill. And the pill had other fillers besides lactase in it, so those are all going to separate to the bottom. And then on top is going to be the water, and we're going to be able to then, which contains our lactase. We're going to pull a sample of that off and use it. All right, so we're going to do this for a minute, and you can hear it running. And in just a second, you'll hear the minute timer click off, and we're going to allow this to slow down. So as this is decelerating, you can hear it decelerating. We want to make sure that we wait till it always at the end. And this one has a lock, and you can hear the lock click, and that means we're allowed. So this is to take this off, and this is really the safest approach. So again, we have our microcentrifuge tube, and notice we have our white solid. It's sort of stuck to the bottom and the back side as it was spinning around. And we have some liquid that's above it, and that liquid should contain our lactase. Now again, with the solid remaining is some of the fillers that is needed. We don't really need much lactase in our bodies, and so even in the pills, so much of that is filler just to help us have a hard tablet. So I'm going to set our automatic pipetter to 500 microliters, and then we're going to pull out that 500 milliliters, and put it in to a tube I've labeled extract. And this is going to be our source of lactase for the rest of the experiment. We're going to use small amounts of the lactase, and this is going to be the source from where we get it from. All right, so this is our lactase extract, and we're going to use this in the next part of the experiment. Okay, so in the first part, we got our source of lactase, and now we have an enzyme. What we're going to do now is we're going to observe the assay. That is the test for the presence of lactase. Recall, we're going to use this compound called ONPG. ONPG is a compound that will become colored when it actually is acted upon by lactase. And so we're going to observe that and see what color it actually forms. All right, so we have our source of lactase. So we want to develop our assay. So first we need to have the bulk of our solution, and that's going to be buffer. So proteins and enzymes, as we know, like to have a very particular pH. So I'm going to add 390 microliters of the PBS, the phosphate buffered saline. It's a pH 7.5, so I added 390 microliters of it. Next, I'm going to add our source of compound. This is the ONPG. We're going to add 100 microliters of the ONPG. So that's going to act as our substrate in this assay. So we've added that to our compound. And then now what we want to do is add the lactase. So we have the bulk solution, the phosphate buffered saline. We have now our substrate, the ONPG. And we now want to add the lactase to it. So we're going to do that. So this is the lactase that we isolated in the first part. I'm going to dump that over, open that up. And we're going to add 10 microliters of the lactase. All right, so it's going to be a total of 500 microliters, but most of it's the phosphate buffered saline. We have 100 microliters of the substrate. And now we're going to add the lactase, and then we're going to observe this for a change. This is what's called a colorimetric assay, and it actually forms a color. So we're going to put that in, and then we'll mix it up just a little bit. And notice that it sort of starts out at a nice clear solution, just looks like normal water almost, but we're going to allow it to develop. And usually we only need about a minute to 2 minutes or so to get the color developed, and so we'll let that go for just a second. And perhaps as this is starting to turn a little bit, if I just hold up a white background to it, maybe you can see that then there's a little bit of a color contrast that's coming. So at this stage, what you can do is, as we're watching this, just think about the time period, and also think about the color that this is becoming. And I'm going to give it one more mix, make sure we have everything mixed up. All right, so I think that's to make it a little bit darker, but not too much. What we've done here is been able then to develop a little assay, right? That is a test, a simple chemical test for the presence of lactase. And so lactase catalyzes this breakdown, and once we form the ONPG, it's broken down into the lactose and the orthonitrophenol, then what we have is this nice yellow color that forms, and that's a nice visual test for one of this. But then also we can use a spectrophotometer to sort of quantitatively measure how much of this is produced. And we're going to do that quantitative measure in the next part of this experiment. In that first part, what we did is we looked at really the effects of lactase on the ONPG. Now, a good question to ask yourself would be, is it lactase, or maybe just ONPG in solution, it just breaks down? Because sometimes we know the compounds do break down in water. Maybe it was the temperature. Maybe it was something in water. Maybe it was a natural hydrolysis reaction. All right, so for that purpose, we need to make sure we control for that possibility, that the compound just naturally turns yellow after some time. So that's what we're going to do in this section, is we're going to look at a control, basically the same mixture without the lactase, and then we'll look at the mixture with lactase. All right, so we'll have a control, and what I'm going to call reaction A. All right, so we're going to compare those two. So we have very similar compositions, but we're not going to put lactase into the control. So into the control mixture, what I'm going to first put in is 400 microliters of the phosphate buffered saline. So I'm going to put 4 of it in there, and to let a little bit of it just spill out. So I'm going to dump that out and make sure that we have the correct amount. It's always important that we're quantitative. So put 400 in there for the control. Now remember, for the reaction that we used last time, we used 390 microliters. We're going to use that again, because remember that other 10 microliters is where we put the lactase. Some of that to bring a total volume of 500 microliters. And recall the control does not contain this lactase. Both of them get equal amounts of the ONPG. And make sure our tip stays on. And so we're going to put 100 microliters in the control tube. So that gets the ONPG. And we also get that here in reaction A. So we have those two. Now, so what we want to do is for the reaction A, we want to make sure that we mix in 10 microliters of the lactase that we extracted back in the very first part. The extractions. We're going to pull out 10 microliters of the lactase, small amount, you can barely see it, and we're going to put that in. And then what we're going to do is we're going to just give them each one of these guys a quick flip, so just to mix it up. All right, so we can use a vortexer, sometimes it's just easier with small volumes, just to mix them up. And then we're going to start a timer for 1 minute. All right, so we're going to allow this to react for 1 minute, and then we're going to quench the reaction after that 1 minute with some sodium carbonate, which basically just going to change the pH and it's going to stop the reaction from occurring. All right, so for each one of them, we're going to let them mix for a minute, and maybe we can even sort of get a little look at one of them. So again, our reaction with the lactase, notice it's getting that characteristic color, and then also notice then that our control, here as we're allowing temperature, is probably staying a little bit more clear, right, as we would expect. Now again, remembering that this one that's remaining clear does not contain lactase, and that was intentional because we want to see the impact of just sort of natural temperature and natural conditions on the OMPG to make sure it's just not naturally falling apart and forming this yellow color. Right? And so that's what we're doing. So we're going to let it go for a minute, and then once we get the minute gone, we'll make sure we stop the reaction so to stop any formation of any yellow that would form. So after our minute, we're going to open these up, and then we will add 500 microliters of sodium carbonate. And again, the reason for the sodium carbonate is a source of pH change, and we'll mix them up. Again, that's always such small liquids, we can actually just flick them a little bit, and that's going to quench the reaction. That is, stop it from occurring, so stop the lactase from actually working. All right, so just need to make sure it's mixed up, and when we do that, boom. All right, so that is good. So now it's quenched. Now, we can see, as we said before, that one turned yellow and the other one did not, so the control really didn't turn yellow at all, but the reaction for 1 minute did. So we can see that just visually, but it's also good to be able to measure it quantitatively and experimentally. So for that purpose, what we're going to do is we're going to use this guy, our spectrophotometer. The spectrophotometer is set to 420 nanometers, and so that's going to absorb the intensity of that yellow light. Now, you might say, well, hey, the control doesn't have any yellow color, why are we going to measure it at all? The point is that we need to be able to have what's the background. Maybe there is a little bit that's formed, we just can't see it, we want to measure it. All right, so we're going to use this spectrophotometer. That's sort of a classic undergraduate high school sort of spectrophotometer, which measures the absorbance of light at 420 nanometers. So to do that, one of the things that we need to do is we need to blank it. All right, so we need to make sure that we need to make it blind to the effects of absorbance due to water, or in this case, our water with a buffer in. So we're going to put in some water into this little cuvette. Again, a cuvette is made of glass, quartz, and the light's able to go through this. And so we're going to, in order to use the spectrophotometer to do this, we have this special little holder that we have. And so then we're going to have the solution in this cuvette. We put it into this holder, and we're going to open this up, and then we always enter it this way, so the light is going this direction. So we want the little source of light where it's not black to be in this direction. And we're going to put that in the instrument, close the lid. It's set to 420. I'll make sure that it's right at 420. And then we want to blank it. All right, so this is 0% absorbance is what we're really measuring. And so we're going to hit the button, and it'll say BLA is really what that's supposed to say, and it stands for blank. You can see that it's flashing, and this is just telling the user, hey, we're actually blanking. All right, so we're going through a process where we're making this instrument blind to the impact of water. So you can see it goes straight to zero. That's zero absorbance. How much light is absorbing at 420 degrees? I'm sorry, 420 nanometers. Right, 16 degrees. So what we do is then we'll take our cuvette, and we'll add the control to it first. That is the 500 microliters of this. We'll add it to our cuvette, and this is going to give us the impact of then the solution that's here. Right, so we'll put that in our holder. Make sure that's set properly, and we'll put that in, and this will be our control. So what you'll notice is that the control, it has this value. Notice it says that it's negative 0.003. So we should write that down, but we should know that really, this is really zero. We can't really go negative, but it's there. And actually notice that it's bouncing around a little bit, so maybe we'll change that and we'll call that negative 0.004. But effectively, whether it's negative 0.003 or 4, you can't technically have negative values, but for the instrument, we'll set that. And so we need to then adjust our sample of reaction A for this control, because the control is not absorbing, and in fact, that would tell us that it's sort of not an anti-absorbing, which is not really possible. So what we do now is we're going to take our reaction A, and we're going to put some of it in. This is the yellow color, and we'll be able to see that visually, see that it's yellow. But then also, once we stick it into the spectrophotometer, we'll be able to measure the amount of yellow quantitatively. All right, so as we stick this in, what we notice that our value is 0.089, so it's a positive value, 0.089. And again, these units, technically we can call these absorbance units, so AU, but it's basically the amount of absorbance by this instrument, and so it's not really like grams or anything else, but we refer to them as absorbance units. So we can see that adding the lactase broke down enough OMPG that our absorbance at 420 nanometers is 0.089. The control actually was slightly negative, negative 0.004, and which effectively means it's not absorbing at all. All right, so this part was really looking at the impact of the lactase on a solution of OMP versus the control. And what we can confidently say is that the control with no lactase really didn't find any OMPG that was broken down and turns yellow, either visually by looking at it or by our spectrophotometer. Neither one of those detected that. However, the solution that did have the lactase in it did turn yellow. We could see that visually, and we're able to measure that at 0.089. So that's really looking at the assay, controlling it for the effects of lactase. What we're going to do in the next part is we're going to look at the impact of temperature. How does the temperature, the room temperature, hot temperature, cold temperature, how does that impact the performance of lactase? In this part of the video and experiment, what we're going to do is look at the impacts of temperature. So temperature is right around where humans and other organisms would likely exist. And we're looking at the impact of how that affects then lactase and its activity. So we're going to repeat the last experiment, but we're going to do it 3 different times. We're going to compose one. We're going to do it at on ice, that's 4 degrees Celsius. We're going to do one at room temperature like we did before. And then we're going to put one in this water bath that's about 37 degrees. All right, so let's go ahead and conduct our experiment and get this going in terms of the volume. So again, for the controls, we're going to have, again, 4 degrees room temperature and 37 degrees in terms of our 3 temperatures. We're going to have control at each one of those. So we need to treat with a control. We need to treat it otherwise just like we would our experiment, except in this case it's not going to have lactase in it. So that means we're going to put 400 microliters of phosphate buffered saline in each one. So control for the 4 degrees. The second stop on our pipetter, the room temperature, the 400 microliters of the phosphate buffered saline, and the same thing for the 37 degree. Now for each one of the 3 samples, we want to put 390 microliters of this phosphate buffered saline in each one of our reaction tubes. So that's good. We need to add our source of substrate, and that's the OMPG, so that's 100 microliters. And again, each one of the tubes gets that because we want to make sure that we have our source of substrate in each one of the tubes. So all 6 tubes get this. that's the substrate. Now we also need to add our extract to the reaction chambers for the 4 degrees, the room temperature, and the 37. And these are the guys that react. Remember, the control do not get the lactase because that's we're controlling, making sure the impact of anything killer that we see is on the enzyme and not on anything else like temperature or just natural degradation. All right, so we've added the extract to each one of those. So we put that down. And then we need to take each one of these tubes. We need to put the lid on it. We need to give them each a quick vortex. Again, with small samples, sometimes it's easier just to mix them by hand. And then once we get this 37, once we get that mixed, what we're going to do is go ahead and these are all at room temperature, and we're going to start our timer at this stage, and we're going to take our 37 degree, we're going to put it into this water bath, which is close to 37 degrees, a little bit on. And so we have this little floater, and we're just going to let it float in the hot water. Put the lid on there, try to keep it at 37 degrees. We're going to take our ice cold ones, the ones that are really at 4 degrees, but the 4 degree reaction tube and the control, we're going to stick it in to the ice. And then these other two, which are room temperature, we're just going to leave them out. All right, so they're just going to be at normal room temperature, and we're going to let them all go for approximately a minute. Then when they come out of their temperatures, we're going to add the sodium carbonate to those to make sure that we're quenching the reaction and stopping it further from forming. And then ultimately what we're going to do is, we'll, just like before, we'll sort of visually we'll see that some of them are reacting, but then we'll use our spectrophotometer here to actually measure the values of those at the specific ones. That'll give us some quantitative measure of what we're doing. All right, so that's been a minute. So let's go ahead and we'll pull these out. So we have 4 degrees. Put those up. And again, because we're taking just a little bit of time, it'll be just a little bit over, but we'll try to add our sodium carbonate to quench anything pretty much as fast as we can. All right, so we'll do that. So we've got those, and again, we'll want to mix them up just a little bit. And so again, what we can notice is that, once again, against the background, we can see that the yellow one was one reaction, and then the clear ones are control. And this is for the 37, and if we compare the 37 to the 4, we might be able to see just a little bit of difference in terms of the color. The 37 might be just a little bit darker, but to be sure, we want to actually take some measurements to see what those values are. So we're going to use the spectrophotometer again for that. So we've already blanked it with the buffer, as we did earlier. And so what we can do is each one of these temperatures has their own control. So of course we'll start with the 4 degrees one. That was the one that's on ice. We're going to get the absorbance. And again, remember that we want to always get the control value for each of the temperatures since they're at different conditions. So we'll take some control, stick it in our cuvette, and to our spectrophotometer. And notice for this one we get about 0.017. Right, so that's the absorbance of the control at 4 degrees. And then we can get our sample. And so notice this one is about 0.209. Right, so we see that value, and that's again for the 4 degrees Celsius. So make sure to wash in between with just a little bit of buffer, since we do have some yellow formed previously. And the buffer is what we blanked with. All right, so now we'll try our room temperature. And once again, we will work with the control first at room temperature. Right, and notice that again, the absorbance for our control at room temperature is negative 0.001. We can write that down, but just recall that that's really close to 0, and so it's hard to determine. So again, that's room temperature, control. And we can then do the same thing with our room temperature value that contains lactase. So this is our reaction tube, as we might call it. Okay, so at room temperature, notice the value is about 0.275. All right, so just about the same as the 4 degree one. So that one's just slightly less. So really similar values for the 4 degrees and about room temperature, which is again close to 25 degrees in here. And then lastly, we'll again wash with our buffer, but then measure the control at 37 degrees. The absorbance for this one is 0.10, so this one's a little bit higher, 0.10. Did you notice it's flickering, so can't decide if it wants to stay at 10 or 11. All right, we'll call this one 0.011. All right, so we'll just go with that 11. And sometimes spectrophotometers, they do bounce around a little bit, but we'll go with a slightly higher value just to be more conservative. And for our control, for 37 degrees, we'll put this one in and measure it. And notice that its value is 0.305. So it's certainly a higher absorbance than the other two. And again, our 4 degrees room temperature, we're very close, but this 37 degrees is significantly higher, so 0.305. So as you can see, for the ice, one that was on ice, one at room temperature, and the one at 37 degrees, there were different values. Now for each one of those, we got a value of the absorbance of the reaction and a control. And you need to make sure you subtract the control from each one of those values to get the actual true absorbance. But the general trend that you notice in all those cases is that the one on ice had the lowest absorbance, less reaction. The one at room temperature was somewhere in the middle, and the one at 37 degrees had the highest absorbance overall. And so again, a higher temperature, the lactase was more active. So with that, look at temperatures. The next part that we're going to do is we're going to look at really high temperatures, that is denaturing the enzyme, and see what impact that has on lactase activity. So we've seen the impact of ice cold temperatures, room temperature, and 37 degrees, about human physiological temperature, on the reaction rate of lactase and its activity. Now we're going to look at boiling water to see what impact that would have ultimately on the structure, the thermal denaturation conditions for the enzyme itself. So let's go ahead and construct a control and 100 degree activity in much the same way that we have previously. And so again, for our control, we'll have 400 microliters of the buffer, 390 390 for the 100 degrees reaction temperature. Then we'll want to put in our ONT substrate for each one of those. And then finally, we'll need some enzyme, right, for the one that we're labeling 100 degrees. Right, and actually, before we do that, one of the things we're going to do, so we've got the buffer and we have our LNPG, and actually what we're going to do is we're going to pull this out and we're going to boil the enzyme itself. All right, so we're going to take our lactate extract that we did before we put it in here. We have that all set up, and we're going to set it in the buffer, or in the sort of boiling water bath. And so we're going to boil the enzyme for 10 minutes. Right? And we're going to let it heat there and see how it works. And then once we finish those 10 minutes, what we'll do is we'll come back and we'll add that enzyme to a reaction tube, and then from there we'll conduct the experiment. Okay, so we have our control and reaction microcentrifuge tubes that we put together except for the enzyme. And so the enzyme, what we did is we took a whole tube of enzyme that we ever made, and we put it into this boiling water bath, and we left it there for 10 minutes. So we're going to pull this out, and this enzyme then is going to be our source that we're going to use for the final step to add enzymes to the reaction tube to get it to react. So right now we pour it off of this, we turn off our hot water bath, and we're going to let it cool down for about a minute. And as we're letting it cool down, that'll get it back to room temperature. And so then we'll run this same reaction now at room temperature that we did previously. However, what we'll do is now we have an enzyme that's been heated to these thermally denaturing conditions. Now again, what are thermally denaturing conditions? Well, it's about 100 degrees in hot water heated up, water heated to this boiling point. This is really akin to maybe what you do in the morning when you fry an egg. Or you fry an egg is that you crack the egg, you put it to the skillet, right? And if it's a sunny side up type of egg, right, so it'll be nice and clear. But then after you're frying it for a little bit, you've added enough heat, and the proteins start to denature, they start to fall apart. And then they start to precipitate, and they come together, and that's why they ultimately become white, because you have basically solid protein now. It's no longer in solution, forming the egg that you eat for a typical sunny side up type egg. And so that's what we've done here. We've heated this lactase to really high temperatures, and now we're pulling it back down to room temperature, and we're going to see how well it works. Right, so just by touch, as I pull it out of there, yeah, it's not really cold, but it's, I would estimate it's about room temperature or so. So what we'll do is we're going to use our little tube, so this will be our enzyme extract. And really our control is ready to go because it's got the full amount. The only thing we need to add now is a little bit of this extracted enzyme that's been heated to 100 degrees. And we're now going to take 10 microliters of that as we've done before. We're going to add it to our 100 degree reaction sheet. We'll give this guy a little bit of a mix, just like our control will mix that up. And so now we're going to time this, and we'll go for about a minute as we've done before. And we're going to let this go for a minute to react, and then we'll measure the absorbance for both the control and also the 100 degrees after a minute. So it's been about a minute, and as we do before, we will measure our control first. So we'll take one out of this, of our control, and we'll add it to our tube. Give that tube. And we'll put it into our little holder here that we have for it. We're going to measure its absorbance at 420 nanometers. And once again, what we'll see is that it's fairly low, so 0.00, we'll go with 6, since it seems to be a higher number. And that's our control is 0.006. So we'll pull that out. And so then now what we'll do is we'll take our control. So one of the first things you'll notice about the control, take 100 degrees after the control. One of the first things that you'll notice, just color-wise, is that you really don't see much of the yellow. It appears to be a little bit more clear. And we'll take some of this just so we can measure it. Put this in our cuvette. Our spectrometer, again, 420 nanometers. And again, notice what you see, it has a fairly low absorbance, 0.02, call it 0.023, so that'll be slightly higher. And again, it's not exactly the same as the control, but it's significantly less than the values that we saw, even for ice or for room temperature, certainly with 37 degrees. So really, I'll call this almost zero, but it's really just a little bit of absorbance higher than the control is. Right, so in this particular case, what we've seen, these were denaturing conditions. And really what we found out that for heating the protein at 100 degrees for 10 minutes, that seemed to change somehow. Right? So there was a significant difference in the absorbance at 420 degrees when compared to the room temperature where we didn't do that. And likely what that means is that the lactase was unfolded under those denaturing conditions, and that's structurally changing, and was not able to refold so that it could actually have the same function as it did before. Right? And this is actually fairly common in proteins, is that if you heat them too high, they can actually unfold. Again, the cooking the egg was an example of it. They unfold and they precipitate, coagulate, and so this then renders the enzyme useless. Now, some enzymes are able to be heated up to really high temperatures and then able to refold once they're cooled down. But those are some. And for instance, some organisms that live in hot springs, they can do that, so they actually survive at really high temperatures because the proteins are very hardy, and they can actually unfold and refold, or they can just stay for a much longer period of time. In the case of lactase, however, that doesn't seem to be the case, and this 100 degree temperature rendered it inactive.